All right, so you guys, I sent you an email this morning. Yesterday's video. So I was trying those new headphones, and when those headphones turn off, it automatically turns off my recorder. So they died about halfway through. So it didn't record, and the reception on it wasn't very good when I moved like 30 feet away from my computer. It starts cutting it out. So that video was just worthless. So. Yeah. Didn't think though that it'd be a big issue. So that's okay. I think there's enough videos there that I've already got up there for you that you could manage the additional resources that in case you missed anything from yesterday. Yes.
Is our class or your class your course?
Yeah. Yeah.
Do you feel like before, if it's missing like the second one, then you just like move 3 and 4 upwards? So like
So what? 4.
The 1, 2, 3, 4, like the
Okay.
steps you take.
Yeah.
If one of them is just missing, like it doesn't reflect.
Yeah.
So 1, 2, 4.
Yeah. Okay. Yeah. All right. So the one thing I want to talk about for that, and we mentioned it yesterday, is that for that first one, and this is just a reading thing, a mathematics reading kind of practice. When we look at this one here, this is for f of x, if f of x plus a. So you're taking and you're doing something to the x value before you run it through your function. We talk about that being a horizontal translation. And we know that f of x plus a, if a is greater than 0, so let's say a was 3, we'd have f of x plus 3. And that notation tells us to move it left. Okay? But if a is less than 0, so we have f of x plus, still plus, but a is now negative 3. How do I rewrite that? Yeah. Okay? So that would move it to the right. Okay? So it's still defined as x plus a in the image. Okay? But then when we say, well, a is positive or a is negative, it's going to make it look like x plus 3 or maybe x minus 3, depending on what kind of number a is. That's just something I think as you move on through other courses you might see, and you actually have to maybe do a little bit of specific value work to recognize the representation that you might get to make a distinction about what is actually happening. Okay, so if it's plus a number inside there, you move it to the left. If it's a minus a number inside there, you move it to the right. Okay, vertical translation, same kind of idea. Okay, from adding a. Okay, so adding a to the entire function. Ultimately, if we think about it, this is our y value here, right? F of x is our y value. You're adding something to that y value. Okay, we don't do anything to the x, so it moves it either up or down. If a is positive, the f of x plus like 3. Okay, moves it up 3 units. If it was negative, it would be f of x minus 3, or plus or negative 3, and that would drop it. Okay, so move it down. The reflection, you got a vertical reflection and a horizontal reflection. A vertical reflection is the idea that if, let me kind of draw you a quick image here. Say I have a piece of paper here, and I've got like that parabola, and I want to reflect it over the x-axis. That's my x-axis. Do you see how I can fold my graph, fold my paper in a vertical nature, and that will give me then that curve there? Does that make sense? So a lot of times because that graph moved or kind of changed in a vertical nature, we call it a vertical reflection. Sometimes we refer to, when we're done, both those graphs together would have what maybe called vertical symmetry. So the same thing happens, and when we reflect across the y-axis, things move from maybe the right-hand side of our xy plane to the left-hand side of our xy plane, or vice versa. That's a horizontal reflection. But multiplying by a negative out front of the whole thing impacts the y. changes the y's by a negative, so it makes them jump across the x-axis. If we multiply the x by a negative first, okay, multiply this by a negative first before we run it through a function, that's actually going to make it jump across the y-axis. Okay. The reflection process can be a little bit confusing if we don't pay attention to a particular order. Okay, we see those steps down there at the bottom. Those steps are important. I think those are the safest things for you to do in that order, because if I do if my function has a vertical translation and a x-axis reflection together, I actually have to, the safest thing to do would be to do the x-axis reflection first and then translate it up, okay? But what that does, if I don't go in that order, if I do the vertical translation first, I actually have to slide my axis up too, because my axis of symmetry, my x-axis here, let's say that I have something like, we kind of talked about this yesterday. Let's say I have the opposite of f of x plus 3. If I want to take my function and slide it up 3 units and then do the reflection, then my x-axis needs to be split up 3 units too, and then I reflect over that new line of reflection. Does that make sense? Okay. Where if I do this first and then move it up 3, I don't have to worry about the axis moving. Does that make sense? Okay. And it's this idea here, guys. If I take, let's do a function here. That's x squared. If I take negative x squared plus 3, okay, the idea here to get this done correctly is that we started with this function here, okay, flip it over the x-axis, so it would become that blue one, right? And then take the blue one and slide it up 3 units, becomes the red one, right? That's what we want, okay? Where if I move this thing to get this what I want, okay, get that function that I want here, okay? If I were to do the translation first, if I were to do x squared plus 3, so I move it up 3 units first, it would give me that purple one, right? Do you see if I want to get the orange one, I would have to reflect the orange one across that line there. Does that make sense to everybody? So that is why we have a particular set of steps that we want to transform in regards to, so that we don't mess that up, okay? Because if you just kind of haphazardly choose your transformations in any order that you want to, you're probably not going to choose the right order, okay? When we get to a horizontal reflection, in a horizontal reflection, the translation needs to be done first, and then you reflect it. So it's kind of backwards of what we just talked about, okay? So in order to kind of compensate for having to think in all of that, those different manners in regards to whether I've got horizontal translation or in a reflection or a vertical translation and reflection, or maybe we have all 4 of them together in the same graph, that's going to be messy, okay? So when we get down here, we'll talk about why these are a good set of steps to pay attention to. These two here, if I multiply the entire function by a, that means you're multiplying your y values by a. So that's the only thing that changes is your y value. If you multiply by a number bigger than 1, take any number you start with, multiply by a number bigger than 1, it's going to make it grow, right? Okay, it amplifies it. So that'll make your y value stretch. If I go between 0 and 1, it's essentially dividing, and then that's going to shrink my y value, make them smaller. Okay? And then conversely, when we talk about multiplying the x's by a and then running through our function, that then means when a is bigger than 1, okay, your x value that you're going to run through is now larger than what you chose, and that's actually going to compress your figure. We'll talk about that visually here in a little bit. When it's 0 to 1, when a value is 0 to 1, it's going to stretch it to a 4 part. Again, I think we talked towards the end of the period yesterday I don't know what's going on, guys. I'm either losing my voice or finally hitting puberty, so I apologize. If we look at this function here, let's just go x cubed. Okay, there's some key points on x cubed: 0, 0, 1, 1, 2, 8. Okay, those are some key points. And I want to kind of focus in on 2, 8 right now. All right, so the algebra as well here. If I were to take the x cubed and just write it as 2 times f of x. So let's take in your y values and double them. You can see that's what happens here, right? They put the 2 out front. Okay. So what happens then? The y value is double. So this point, there should be on my new curve, on this orange one, the maroon one, we should have the point what? 216. So if I graph 216, let's see if it's up there. Absolutely. Okay, so C and D correspond, right? Let's talk about how that's different from taking an f of 2 times x. Now it's something like that, right? So this multiplier out front of my, and you can rewrite this, usually we don't. That multiplier out front, instead of really being 2, it's actually what? Is that 2 cubed, x cubed? So it's 8x cubed, right? So now I'm actually increasing my y values by 8, right? Okay, so I'm going to think it that way. Or I can think it this way. I can say, okay, so this point of 2, 8, okay? Then when I actually evaluate, I'm not evaluating at 2, okay? I'm not cubing 2, I guess I'd be cubing what? When x is 2, I'm cubing 4, correct? So 4 cubed is 64, right? So I should see on that new curve, it says 216, I now see 264, okay? Now, if we were to put all these up here together, 2 times f of x, all right, so zoom back into the standard view. So this is, the blue one is your original, okay? Do the other two look like they behave the same way? Okay. In regards to a transformation, the other two look like they're both maybe vertical stretches, or they both look like maybe they're horizontal compressions. Kind of hard to differentiate, right? Unless you have the specific ordered pairs, it's going to be really hard for you to decide that, okay? And to be honest with you guys, if we do a little bit of algebra, this one becomes, you know, that green one is 8x cubed. So it would give me that one. So maybe we do kind of look at that and say, well, it is a vertical. Both all of them are vertical stretches. That kind of makes sense. Obviously, it's a different stretch with an 8 than it is a 2. But that's kind of hard to decipher and determine looking at a graph like this. So when we want to talk about horizontal stretches and compressions, guys, the number one time that we talk about it is when we deal with what we call periodic functions. Okay? And you've seen a periodic function already in this course. The other day we saw this thing. Okay? It's just maintaining the same behavior over and over and over and over again forever, right? Okay? So if I were to put some number out front, okay, so that's going to multiply my y values, right? So look at all my y values, y value 1, y value 2, y value 3. If I start to amplify those, we had a y value of 3 at one point, so now we should have a y value up at 6, right? We had a y value at 1, so we should have a some y values at 2. We had y values at 2. We should have some y values at 4. Does that make sense? All your y values, right, when I adjust it, your y values are the only things that are changing, right? Okay. How does that differ from when I put the a right here? There we go. So when we have a to be 1, okay, that's the floor function. But now when I make a bigger, now when a gets bigger, are your y values changing? No, it's your x values, right? And it's compressing, so when a is larger than 1, it's a compression, okay? But when a is between 0 and 1, you see how those segments all stretch now? Okay, y values are still the same, right? Okay, so that's the idea of dealing with horizontal and vertical compressions with periodic functions. I think I showed you guys a sine function maybe yesterday. Here's the cosine function. That's periodic. As far as I zoom out, it's fine. As far as that end and the other end of the x-axis, we'll get the same behavior. So it's kind of easy to see then that when I multiply this by, I don't know, some value a, I get that. You see it, that is, you know, the tops and the peaks and the valleys of the green curve have been stretched, right? Okay. Where if I put that 4 here, now you can see that I put my hand on the ends of the green curve and push my hands together. That green curve is going to kind of bend in on itself, right? Kind of like almost like a slinky type idea. That's much easier to determine the logic or the understanding of horizontal and vertical compressions, and differentiating them, determine which one's which when we deal with periodic functions. So this will be an aspect of trigonometry when we get there. All right, so that brings us to the blue box. The idea, and it's because of the reflections here. The key thing is to want to do those in those orders, or that order, okay? Now what Emily said is, if one of those is missing, do we just go to the next one? Absolutely, okay? My suggestion to you guys, I just remember the phrase HSRV, okay, or the acronym HSRV. And every time I come across a function, that's how I'm going to address it, okay? I want to show you kind of the benefit of knowing these transformations. But before we get there, I want you guys to look at this, okay? And I'll show you on my website where this PDF is. These are what we call parent functions, okay? And we're going to build upon the parent functions that we know. You know about probably 2/3 of these on this page right now. But these are the most simplistic versions of types of graphs that we deal with. We've dealt with linear graphs, we've dealt with absolute value, we did the greatest integer, we've dealt with quadratics and cubics and cube roots and square roots, okay? But these are the most simplest looking version of those, okay? The constant one's really not that interesting in regards to transformations. You can reflect it by multiplying your a by -1. You can adjust your y values, but you can't really do anything else, moving left or right or anything like that. There's no x to deal with there. Linear functions are kind of boring, but you guys, now I do want to show you something with linear functions. You guys have probably been taught, you know, y equals x is that thing right there. Right? That's our most fundamental linear function. And you probably introduced translation by doing that, right? And saying, well, I knew 0, 0 was on that line. 0, 0 is here. You knew maybe 2, 2 was there. So then, if I look at that, it is adding to our y, right? This is, you know, f of x is just x. This is f of x plus 3. That's what this horizontal is. So say, take your y value, add 3 to each other. Add 3 to that y value, I get 0, 3, right? Add 3 to that y value, I would get 2, 5 right there. And now I've got 2 points plus x to your line, right? Okay. So we use transformations that way. But what you guys probably haven't been shown is if I do this. Now think about what I just typed in there. X plus 3 raised to the first power. Is that first power really going to do anything? No, right? But when I hit enter and it shows that, maybe it might help you realize that not only is this here, when I look at it this way, adding to the y after I evaluate what my x value is. This here is adding to my x, and then running it through my power of 1. If I have x plus 3, doesn't that move that point 3 years to the left? And doesn't it move this point 3 years to the left? Does that make sense, everybody? Okay. That's just a situation that you see with linear functions, is that you've always been taught that when I go x plus 3 or x plus whatever, it's sliding it up or down, right? Okay, because that's how you dealt with your y-intercept. We also see the relationship that it can actually be moving it left or right instead. Okay. When we deal with the absolute value function, guys, each one of these, there are some key points that we want to kind of commit to memory. Okay, so 0, 0, I would go maybe 4, 4, just knowing I'd go 1, 1, 2, 2, 3, 3, 4, 4. These are going to be negative, and then the positive, right? So negative 4, positive 4, negative 3, positive 3, negative 1, positive 1, that kind of thing. So knowing a handful, knowing at least 3 points on that is going to be useful. The greatest integer function, I'm not going to spend a whole lot of time on, what 3 points or what series of points we need to know. Essentially, what I always do with the greatest integer function is I try to find through evaluation what the first 2 kind of steps are, and then I just repeat those steps over and over. Okay, and that will give me the rest of the function. The quadratic function, okay, now here you probably want more than 2 points. You probably want more than 3 points. We like 0, 0. Probably got 1, 1. And we've got 2, 4, right? Okay. Now, something we'll talk about at the end of the period today is that this thing it's got symmetry across the y-axis, right? So here's the nice thing, is that I could just commit these to memory with the fact that they're symmetric about the y-axis, and that automatically generates these points for me. Right? Okay. But those are the 5 points off that parent function that we want. These 2, or this 1, I guess, the cubic function here, x cubed. We want 0, 0. We've got 1, 1. The next one will be 2, 8. And we have negative 1, negative 1, negative 2, negative 8. I think those are 5 points that we should commit to memory on that one. And basically what I'm doing here, guys, is I'm just looking at x values of 0, 1, and 2, negative 1 and negative 2, and evaluating, right? These y values. But my hope is that we can start to memorize those pretty quickly and don't have to do that kind of T-chart mentality to remember what the points are. 0, 0, 1, 1, 4, 2, 9, 3 would be another one, right, on the square root. The cube root. So the square root, guys, is eventually what we're going to refer to as the inverse of this thing. Okay? We had 1, 1 on that, right? So we get 1, 1 on the other one, on the square root. We had 2, 4 here, correct? We had 2, 4. What do we have on this one? 4, 2, right? See the relationship between those order pairs? So the same thing happens with the cube root and the cubic. Here we had 0, 0. We had 1, 1. We had negative 1, negative 1. The cube root is going to have those 3 points, 0, 0, 1, 1, negative 1, negative 1. But on the cubic, we had 2, 8, right? On this one, we're going to have 8, 2. We also had negative 2, negative 8. So on this one, we're going to have negative 8, negative 2, right? So it's a handful of points to kind of commit to memory. These are, we have entire chapters devoted. Essentially, guys, we have an entire chapter devoted to those 4 graphs. We have an entire chapter devoted to those 2 graphs, exponential and logarithmic. So I'm not going to get into the points that we need to remember on those. And we have chapters devoted to those two. Okay? And then we have an entire course devoted to these three. Okay? Trigonometry is those three graphs and the relationships that we see within those. So the key ones, I guess, those first two rows, hopefully we already know some of those key points because we're going to use those key points. We're going to transform those points. Okay? And then if I transform those points, I've effectively transformed the parent function. Is that right? So the parent function, most simplistic thing, and when we start adding, subtracting, multiplying, dividing, to the x's, to the y's, that kind of stuff, it develops what we call a family of curves. Okay? And a family of curves are all going to have the same general behavior as our parent function. So what I want to do is a few examples of this with you guys. I'm going to start with the parent function. So first one we're going to do is just absolute value of x. Okay? And then I want to do well, look at that. Okay? You'll see people, I always like to do it, I don't like to do it with the T-chart. You can if you want to. But I'm a fan. I'm going to transform these functions. I'm going to look at the graph. I'm going to look at the order pairs on the graph and try to decide, what are these rules doing to my order pairs. Okay? So this is where the parent function stuff kind of comes into play. I want the point 0, 0. I'll pick the point 2, 2. And just to be a little bit different, I'll choose negative 3, 3 there. Those are parent function points, right? So to develop the curve that I'm looking for here in a moment is that I'm going to apply those transformations to all three of those red points. Okay? So let me see if I got enough room here. Not really. All right, so when we're doing this, my suggestion to you guys, write this acronym down. This was horizontal translation. This was stretching, either vertically or horizontal, or both. This is the reflection, and this is your vertical translation, right? Do them in that order, okay? So let's see, is there a horizontal translation? How far? 3, right? Because this is happening to the x. So this is the idea, is that this plus 3 is happening to the x before I run it through my operator of absolute value, right? Before I run it through my function, I'm changing the x right off the bat, okay? So the idea is if I started with, in my original function, x being 0, then I'm actually going to run 0 plus 3 through this before I do anything, right? I'm changing my input a little bit before I evaluate. So I'm going to move it left 3 units, right? So every one of these points gets moved left 1, 2, 3 points, 3 units. Okay? So we see how that impacted those x's, right? Did I impact the y's at all when I did that? No, the y values for those red points stay the same. Okay? Now, we're looking for a stretch. So is x getting multiplied by anything, or is the entire function getting multiplied by anything? No stretch, right? So we just skip that one. Now there's a reflection. The reflection is what type of reflection? X or y axis? It's an x-axis reflection. Okay? It's be multiplied out in front, right? So this one's going to, remember, distance is preserved. So that distance right there to the x-axis needs to be replicated over here. So it gets 3 units down and then 3 units more. Okay? So this one's at 2, it's going to go to -2, right? So now we've done our reflection. Now we want to do our vertical translation, which is what? Down 2 more, so down 2, down 2, down 2. And when we're done, we should be able to see if that graph actually goes through those 3 points, right? So here's the idea, and it'll be a much quicker process when you guys are doing this on your own at some point. You do not want to have to choose a t-chart of just x values. It's okay, I want to choose x value of 1, and then run it through that g of x function and evaluate. It's okay, now plot that point. Now do it with 2. Okay, now plot that point. Now do it with 3, and then so forth. Okay, you don't want to do that. It's time consuming. Okay, so this is an efficiency thing to help us graph these things a little bit quicker. Let's talk about this. Let's see how this would have worked if I just would have gone in any order. Okay, let's just go. I guess let's go left to right. Okay, let's just do what this one says. This one says a x-axis reflection, right? Let's take this blue point, do an x-axis reflection. Now this says to do what? Move 3 units to the left, and now it says what? Move down. So that got me where I needed to be, right? Okay. Let's see if we start here, and let's do this first. Let's go down 2. Okay. Now let's apply the left 3. Now let's reflect it. Stays right there, doesn't it? That make sense? Is that a point that needed to be on this curve down here? What I'm trying to do here, guys, is show you that if I could do these order of transformations in any order, then I should be able to start with that point there, run through them in any order, and that point shows up down here somewhere. Okay, but it showed up. I think it showed up there, didn't it? Okay, is that on the red? No. Okay, so does that prove to you that you can't just haphazardly choose any order you want to? Okay, so horizontal, stretch, reflect, and then vertical. That's the way we're going to address these. Let's do something with x squared. Okay, so let's go. All right. So now we're looking at some key points on that green curve, right? Some key points to that thing. Just to maybe save a little bit of time, let's go to 0, 0, and 2, 4, negative 2, 4, right? The idea, if we just choose 3 points, a lot of people are going to think it kind of looks absolute value-ish, right? Okay, when we get a smooth curve, we do want those points. We'll see. We might adjust those as well, but if we can do those 3, 0, 0, 2, 4, negative 2, 4, we should be okay, I think. Okay? So, again, H, F, R, V. Okay? Is there a horizontal transformation? Yeah. And actually, let me do this in the last one. Let me make sure I get enough room here to those things around. All right. So when we move these black points, we should eventually see if they fall on that red curve. So the horizontal transformation, how far? 3 to the left, right? So that's good, right? So we do the horizontal. Now, is there a stretch? Yeah, there's a stretch. So what stretch is this, though? To the y values, though, correct? Okay, so your y values are going to stretch. So this one's a y value of 1, right? It's going to become 2. This one's a 1. It's going to become 2. Good thing that's what goes in, because this one's going to go off the graph, right? It's at 4. It's going to go up to 8, right? I'm going to write that point there. We'll see if that exists. Oh, that was stupid. There. So negative 5, 8 becomes that point. This one's going to become negative 1, 8, right? All right, so we did that. Now what? Is there a reflection? Okay, so these points are going to get, and that one's going to go down there. That one's going to go down there, right? Okay, is this one going to go anywhere? No, it's on the axis of reflection. It stays there. And then these other ones, so this one's going to be, eventually be negative 5, negative 8, right? Negative 1, negative 8. So maybe that kind of gives you that T chart kind of visual of what we're doing with the X and the Y. So we do the reflection, and now what happens to every point? Down one. Okay, and then this one should be negative 9, negative 5, negative 9, and negative 1, negative 9. So if we graph this, we see our curves, right? If I go find, I'll just plot negative 5, negative 9. Okay, it does show up on this. Okay, so that's kind of the idea that I want you guys to go with and use when you're trying to transform these things. Don't try to pick the entire graph up and move the entire graph, right? Pick up key points. Pick up 2, 3, 4 points. Move those, and that should then give you an understanding of what everything looks like. But you need to go in that order. Okay? We got time. So let's just say that I take 2, 4. So that's that point right there, 2, 4. What did that become? It became negative 1, negative 9, right? Eventually. Let's just kind of go through this to see if we get to the same point just by going in any order. So let's just do this negative here. We're going to take 2, 4 and change it to. What's the negative do out front? Changes the y value, doesn't it? You can take 2, 4, make it 2, negative 4. Now let's take and apply the 2. What's that going to do about y value? Makes it twice as big, right? Negative 8. Now, what does that do to my x value? Yeah, it moves it to the left, right? Moves it 3 inches to the left. So it's going to make 2 what? Okay. And now moving, this is going to make it go up. Down 1. Did we have that point, negative 1, negative 9? Yeah. So that order is okay. Okay. Sorry on it. We set out to do this. I don't know if it would be or not. If we go, so start 2, 4. Let's go in reverse order. Let's drop it down 1 first. Give me 2, 3. Okay. Let's move it left first. For next. Okay. So give me negative 1, 3, right? Okay. Maybe now we reflect it. So when I reflect it, that's going to give me negative 1, negative 3, right? And now I double the y value, create negative 1, negative 6. Is negative 1, negative 6 on that curve? No. Can't be. It's negative 1, negative 9 was. Negative 1, 6 is going to be negative 1, sorry, negative 1, negative 6. It's right there, right? Not on the curve. So you can't just always say, I'm going to do them left to right. I'm going to do them right to left. You got to do them horizontal, stretch, reflect, vertical translation. All right? Okay. Now there are, so this is, we'll pick up with this a little bit tomorrow as well. I want to introduce this to you first today. If I take that graph right there, x squared, okay, now I'm going to look at just the right-hand side of it. So let's look at x squared for x is greater than 0. So just that right-hand side. Would you guys agree that if I take that right-hand side, so the point 0, 0, 1, 1, 2, 4, 3, 9, take that right-hand side, what can I do to get that blue to land on the green? reflect it across the y-axis. So I can take this, reflect this about the y-axis, and it gives me that, right? Okay? When that happens, guys, think about this, and you understand this with your algebra. Right now we have f of x. I'm going to show you what f of negative x looks like. Okay? F of negative x, and I think if I maybe do this, gives me that, right? Would you guys agree that that's f of negative x? Okay? Does it give me the same thing? And algebraically gives me the same thing because what we're seeing here is that when you square a negative, you always get a positive, right? So what we got here, guys, now GeoGebra can't name it for me this way, but this is f of x, and this is f of negative x. Okay, we're seeing those two graphs are what for us? They're the same. So when f of x is equal to f of negative x, what that means to us is that we have y-axis symmetry. Okay? Basically, if you think about that rule, f of x equals f of negative x, it's saying the y value of these two things, the y value of x, whatever that equates to, will be the same as the y value of the opposite of that x, right? So let's look at 2, 4. Okay, so that's x. That's f of x, right? What's the opposite of x? Negative 2, right? You see how this is opposite x, f of negative x? Do you see how that f of opposite of x is the same as that f of x? Okay. When that happens, guys, this is a unique function. Okay, this is referred to as an even function. Okay, and it's basically defined by the idea that we have y-axis symmetry, or by the algebra that f of opposite of x. Okay, but what's nice about that, if I'm able to recognize that a function is even before I graph it, now I don't have to do maybe 5 points on this curve. Maybe now I only do those 3 points. Because now I know if I have those 3 points, because of the symmetry, I can automatically find the other ones on the other side. Does that make sense? Okay? So it's